let's continue on with this concept of statistical hypothesis testing. Last time we talked about the difference between a type 1 and type 2 error and how we have to make those choices. But our chart on the right here hasn't changed. Step 1, we have to talk about what H0 and H1 are. And also we have to discuss what alpha is going to be. Let me find my eraser. Step 2, we're going to calculate the t-test statistic. Last time, we knew information not only about our sample, of course, but we also knew population mean, which was what we're comparing it all to, and we also knew population deviation. This time, we may not know population deviation, in which case we'll have to settle for sample deviation. Then you look up the probability. Again, if we have this, we'll use a normal distribution chart. If we have this, we'll use a t-distribution chart. You make your choice of H0 or H1 about rejecting or not rejecting. In the case of z-scores, we're going to use this p-value that we calculate and compare it to alpha. In the case of z-score, we're going to once again have to calculate a p-value and compare it to alpha. We're going to talk about it in a couple of ways. Modern statistical software does allow us to simply look up a precise p-value for a t-score, but we'll maybe look at our chart that comes with most modern textbooks, because not all calculators have this functionality. Excel does, of course our program does, SPSS, Stata, SAS, all of these have the ability to calculate a precise value for p. In fact, your online homework environment also has the ability to calculate a precise p-value. It has some little slider tables for t-distribution. But we'll talk about the concept maybe with the chart. It's the traditional way to do it. And finally, of course, once you choose to reject or not reject null hypothesis, then you try to sum this up in an English sentence. So I've gone online and found some statistical information about U.S. life expectancy. Things to instantly think about. We know maybe from previous sections that men tend to live not quite as long as women in general. So if I give you a single U.S. overall life expectancy number, maybe that's a little low for women and a little high for men. I found the number 78.61 somewhere on the internet. I don't have ultimate confidence in my source, but having looked at other data, I'm willing to believe this is probably close to being true. Let's say we grab a random sample of 7 obituaries in Texas. And you can't just go and grab them all from one newspaper. Let's say we went and grabbed 7 from around Texas, and we might ask the question, is Texas different from the U.S. normal life expectancy? Now, if this average of 78.61 is to represent a nationwide average and not segregate by gender or other health predictors, because this is sort of one big average, then definitely we should be hoping that as we pick our random sample, ideally we would have people of both genders and sort of all sorts of people. And of course, this is only 7. That's a very bad sample size, but it will let us calculate things nicely and quickly. If I really wanted to make a firm statement of difference, I would probably want to get more than 7. And of course, my random sample should be suspect because I didn't actually look through obituary papers. I just made up these numbers. Though I happen to know a little bit about how Texas works, and so once again, we're going to maybe come to a true conclusion, nonetheless. So these are our steps. And let me encourage you that words matter when you learn things. If you can say the words of what you're supposed to do, then you kind of know what you're supposed to do. So step 1 is where we set up our hypothesis, our hypotheses, and also where we pick alpha. The null hypothesis is always that there's no difference. U of Texas is still going to be 78.61, the same as the rest of the United States. Texas is part of the United States, so it's one big piece of the whole. That's the null hypothesis. No difference, no significant change. The alternative hypothesis is going to be that there is a difference. We have to pick left-tailed, right-tailed, or two-tailed. Now's the time to go ahead and enter these numbers, your data, into the calculator. And if I go ahead and I've already entered them into my data column here, so I'm actually going to go ahead and hit second statistical, pick one variable statistics, and calculate that out. For these 7 data points, I get an x-bar of about 64.7. That seems very different. 64.7 is less than 78.6. I have two options. Notice, the right-tailed test is completely out. 64.7 is definitely less than 78.61, so there's no way I would say it's more. So this one's not an option. Right-tailed is not reasonable. However, depending on our data, left-tailed or two-tailed might be good ways to go. We do have to pick which one we're going to use. That's going to influence how we run our test. So let me give you the rundown now. Two-tailed is always the most conservative. It is the least likely to trigger. If you talk a little bit towards the end of this section, usually is where textbooks tend to introduce the slightly older way of doing this called critical regions. And two-tailed, because it separates the critical regions onto both sides of the normal distribution, our options, if we're looking at this, are going to look like this. Let's go ahead and pick alpha. Let's pick alpha since this, well, it is life and death, I suppose, but it's not really life and death, right? Let's pick alpha to be 0.5. This isn't squishy medicine where we're running tests and whatnot. If I pick alpha of 0.05, then we know the confidence level is 95%. Here's the difference between a left-tailed and a two-tailed test. In a left-tailed test, if alpha is 0.05, then what we're going to compare the p-region that we calculate at the end when we make this decision, we'd be comparing a p-region to 0.05, and we'd have 95% on the left. What does this mean? Well, it means, and maybe I should draw these bigger. I always have this fear that maybe it looks perfectly fine size to me. And I'll erase this and maybe make a smaller one in a second. So let's compare these to large scale. Remember, norm is always in the middle. It will have a score of 0, whether we're calculating t or z, because you always have x bar minus mu. So if we're actually equal to 78.61, this is going to be where mu lives here in the middle. This will be true for left or right. Let's make this the left one, and let's make this the two-tailed. Excuse me, not left or right, left or two-tailed. If we pick a left-tailed test, because 64.7 is smaller than there, even for both of these, x bar is either way going to be on the left because it's 64.7, right? If we pick a left-tailed test, we're going to make the cutoff line be here with 0.05. And then we have to decide which side does x bar fall onto. So maybe I won't commit to where x bar is. I'll just write it roughly over here. We don't know yet. That's the whole point of writing this test, is to find out where x bar lives. Keep in mind, if we have 95% on the left, that's great, but the point is, over here on the right we have 95% total, but we have 0.05 here on the left. If we do a left-tailed test, remember, this line here cuts me in half, so there's a 50% over here, which means there's 45 plus 0.05 gives you your total 50%. Notice, if the x bar ends up, once we do z-score or t-score calculations, ends up falling in this left piece, follow the logic carefully. Half the normal curve gives me 50% on the left of mu. We know our x bar happens to be less than mu, in this case. If we do a left-tailed test with an alpha confidence level of 0.05, then there's a 0.05 chance of landing here, there's a 0.45 chance of landing here, but if we're only looking at the left side, we should calculate these as weighted averages. So 0.05 over 0.5 versus 0.45 over 0.5. If we go ahead and calculate that, of course it's probably pretty straightforward, but 0.05 divided by 0.5 gives me 10%. And of course this is going to be 90%. If we pick x bars at random, under this interpretation, we would be expecting a 10% chance that x bar should fall in this region which would give us a significant p. Remember our type 1 errors, alpha was our level of significance. And this would allow us to talk about this rejecting the null hypothesis. Contrary-wise, as we're talking about this, security's checking up on me, folks, which is great. Contrary-wise, if we're talking about this and we do a two-tailed test, we make our split and we take the 0.05 alpha that we've got and we break it in half, putting half on this tail, 0.025, and the other half on this tail. And that means when we make our cut, we only have a 5% chance of landing here on the left. So what you see is that since we happen to know that x bar is actually going to be on the left over here, if you do a two-tailed test, it becomes a lot harder to get into this region. This region in the old form of doing this calculation, critical region. And of course this would be a critical region as well. So what you find, and critical region and the p-test are two very equivalent, entirely equivalent ways of doing this calculation. But where I'm going with this is what you find is that you're more likely to trigger a null hypothesis rejection under a left-tailed or a right-tailed test. A two-tailed test is not as likely to trigger that. So in addition to picking a small alpha, if you want to reduce a type 1 error, if you do a two-tailed test, you're going to reduce your chance of a type 1 error as well. Because you're less likely to reject the null hypothesis, you're more likely to not reject it. And if I look over my notes from last time, when we do not reject the null hypothesis, and even if it's false, we have that as a type 2 error. And I think where I'm looking for the notes is, I split it up this way, I think, and so we had type 2 errors at the top right. So go back and look at that video and look at the piece at the top right. We've been sliding this around so you can have some choices in how you make this happen. So we have options, is where I'm going with this. Left-tailed or two-tailed. Take a moment and look through this and convince yourself why right-tailed is certainly not possible. It's not legit for this scenario. It can be in some cases, but this one, it makes no sense. Once you've convinced yourself of that, then you see our problem. We have to decide between left-tailed or two-tailed. These are the consequences of these choices. Here's how I go with it. And this is a rough estimate of thumb. At the end of the day, of course, you could always just pick a different alpha instead of doing a two-tailed. I mean, you just slide it around and it'd be roughly the same sort of calculation, I feel like. So, for this class, if it's not a critical calculation, I think that single-tailed is probably a more actionable way to go. It tends to, I think, maybe flow a little nicer. It makes a model that's more clear to understand. It's harder to explain why I would choose to break things up into these two pieces and perform this two-tailed calculation. However, if we've got ourselves, and of course, you're thinking, well, yeah, x bar here, it's on the left, so definitely one of these two. When would I choose to do a two-tailed? Well, what if 64.7 had been very close to 78.61? Then I might be thinking, well, actually, it could actually be bigger. The data could go either way because, yeah, we've got a little bit of a sample that's on the left side, but changing a single point might make it go to the right side. So if I have a small sample size, which I do here, then I start to think, well, maybe I should go two-tailed because I'm not really convinced it's on the left. And it would be unfortunate if it wasn't. I also look in mind and keep in mind standard deviation. We've already calculated x bar, and of course your calculator also will calculate sample deviation, and it's 14.2. little s, let me put this over, let's put it here. Little s is about 14.2. So a rough rule of thumb, and this is very rough, I'm not in any way promoting this as accurate, but for this class at least, maybe what you could do is you can take your 14.2 and try to add it to 64. So if I have 64 and I do plus 14.2, I'm getting 78.9. We have 78.61. So it's very close. This guy's almost one standard deviation in the sample data, at least, to the left. That kind of makes me feel like it's really far on the left, and consequently I'm more willing to go with a left-tailed test. If standard deviation was still 14.2, but the average was, let's say, 76, I would be much more inclined to try a two-tailed test, just because it's a little closer there. It comes down again to just some decisions, and you're coming up with a corresponding greater or lesser chance of calculating a type 1 or a type 2 error. A lot of times in medicine, you see the more conservative you see the more conservative two-tailed test used. For things like this that don't matter, I'm more willing to jump in and risk a type 1 error. So we're going to go ahead and pick a left-tailed test here. Let me go ahead and erase these now. Either one would have been legit, which is why most questions that we assign you probably have to tell you which type of test we'd like you to use. And on the converse side, if you're using a test and you're getting the wrong calculation, then maybe you want to look through the problem and see, did they mean two-tailed and I only use one-tailed, that kind of thing. Anyway, we're going to pick our alpha. Alpha is going to be equal to 0.05, and we've decided to choose a left-tailed test in this scenario. So much for step 1. Step 2, calculate the test statistic. We do not have information about the population deviation. There's nothing on the board that tells me about sigma. Consequently, I am stuck with using a t-test. We know it's going to be a little bit less accurate than a z-score would be because we don't necessarily know about normality. Technically, I should graph these guys out in some kind of chart to try to see, does this data here look normal, but I made it to be normal. So again, in this class you're allowed to kind of assume normality because it's an intro stats course. So we have to calculate t. We know what x bar is. We've calculated it. It's 64.7 minus mu, which was 78.61, divided by sample deviation, since we don't have population information, of 14.2, all over the square root of 7. If I go ahead and plug these into my calculator, fraction bar 64.7. Technically, I shouldn't use 64.7, right? Technically, I should go ahead and use the actual x bar, since I can, and do rounding at the end. Let me show you a little bit of a trick with that. If you go into your calculator and recalculate your one variable statistics, there's the x bar. If I scroll down to that and then hit enter down here, notice your calculator records the x bar right there. I can go ahead and pop that onto the top of a fraction and then do minus. And that way I don't have to remember what the exact number is, and I don't even have to store it in memory. I can just grab it right there. Then we'll do minus 78.61. That was given to us. All divided by another fraction bar, and of course then I'm going to actually type in my full standard deviation. I'm actually going to only type in 14.2 to make it faster, but you should type in the full number and use your record memory feature. Again, this is why I really dislike the calculator, because it's super easy in Excel to just pop in the right equation cell. And here instead I'm having to either use this awful memory feature or type in very long numbers. But I'm getting myself a t-score of about negative 2.589. Alright, so much the same. Step 2 is calculate the test statistic. We looked at our data and decided that we didn't have information to do a z-score, so instead we chose to do a t-score. But now it's time to look at the probability. If this was a z-score, we would look this up on the z-chart, but this is a t-score, so we're going to look this up on the t-chart. And the t-chart works a little differently than a z-score does. Remember, for t-scores, you have to also know, and I hadn't written this down here, but we remember, you also have to talk about degrees of freedom, which is n minus 1. In our case, as part of calculating this test statistic, our degrees of freedom is going to be 7 minus 1, which equals 6. So we're going to have 6 degrees of freedom, and we have a t-score of approximately this. We are doing a left-tailed chart, but we're still trying to look up a normal curve. It's just a t-curve, so it's a little rougher than the usual normal curve, but it still has area of 1 and all that good stuff. If you look carefully at the chart in our book, you'll see that the left-tailed area is talking about with a minus t here, and that's the case for most t-distribution charts, which means if you look on the inside part of your chart, you're going to see a whole bunch of positive t-score numbers and no negatives. That's expected because this is symmetric. We might as well talk about positive numbers and not worry. So you're going to pretend like this is a positive number, and here's what we do. We need to look in the 6th degree of freedom row across our chart. We need to find where the number 2.589 lives, and then we're going to look at the top of our chart. And since it's one-tail area, we're picking the one-tail area. Remember back when we first looked at this in the previous section on confidence intervals, we did degrees of freedom / confidence intervals. But a t-chart normally has about 3 headings to it. So let's take a look. I'm looking for the number 2.589 in the row of 6. So first I find 6 degrees of freedom here, and I follow across. And notice these numbers keep on getting bigger, so I'm looking for when I reach 2.589. And here's 2.4, and here's 3.1, so 2.589 lives somewhere in between these two. I follow these two up to the one-tailed area row, and this tells me that the one-tailed area is going to live between 0.01 and 0.025. So let me take that now and write this down. It writes it opposite, right? In the book, it writes it, in the chart, it writes 0.025 first and then 0.01, but I'm thinking of a normal number line. So I have 0.01 and I've got 0.025. Here's the difference between technology like a program or Excel and looking things up in a chart. For z-scores, we've been able to get a pretty accurate error on the z-chart thing. We're able to get a pretty accurate area. But for t-scores, what we get instead is a little bit of a range. P lives somewhere in here. When you use your homework software, sometimes they'll have little dragger bars of a t-distribution curve, and you can plug in the right data and the degrees of freedom and drag the little slider until it reaches the right spot, and that's nice. But here, it's giving us a p-value inside this range. We don't know what p is looking at this chart. It's not accurate enough, but it tells us where it lives. And we compare this p to alpha. So here's where 0.05 would live. It's bigger. Again, notice when you looked up in the chart, it gave these numbers in reverse order, so you rewrite them on a number line in the normal way. And this is where alpha lives. Step 4 is you make a choice of null or alternative hypothesis. So you make your choice, and you make your choice in the normal way. We're comparing our p-value to alpha. P is smaller than alpha in this case because P is somewhere between 0.01 and 0.025, and 0.05 is very much here on the right side of the number line. There's this gap in between these numbers where things like 0.26 and 0.27 and 0.0239, excuse me, not 0.0239, but 0.0259999 live, and also things like 0.04 and 0.03 and 0.037. So there's a whole lot of numbers in here. P is definitely less than alpha. I'd say less than or equal to because that's how this is. Of course, we know P is actually not equal to. It's strictly less than in this case. But this means that we're going to reject the null hypothesis. So you make your choice, and our choice is to reject H naught. What does that mean? That means that we found statistical support for the alternative hypothesis. Step 5 is to write an English sentence. We'll go ahead and put step 5 over here in the corner so it's a little bit higher so I can write it better. My English sentence is going to be something along these lines, and it's always good to go back to the beginning and take a look. We knew that the US mean for life expectancy was 78.61. We knew that we had grabbed a random sample of 7 people in Texas, 7 obituaries in Texas, and found a mean of 64.7 for the sample. We calculated a sample deviation of 14.2 years. And as we did our calculations, we found degrees of freedom, we found a t-score, we used those to look up a percent chance, we found a range where our p lived, that p was less than alpha, so we've decided to reject the null hypothesis, which means we found statistical support for the alternative. So here's what I say in English. There is reason to believe that Texas has and this is lower, a lower life expectancy than the USA as a whole. That's my sentence. That's a good sentence to make. It's not a very dangerous sentence. I haven't overcommitted myself. I also haven't undercommitted myself. I'm not saying, well, there's nothing to say. There is reason to believe that Texas has a lower life expectancy than the USA as a whole. And that's what our data lets us say. I can't tell you that it's 64.7. If I wanted to do that, well then I should go back to Module 7 and we should build a confidence interval for this. I can't tell you that we could maybe try to figure out some range where the Texas might live. But with this hypothesis testing, I can certainly tell you that because p was less than or equal to alpha, because p was some number in between 0.01 and 0.025, it has to be smaller than 0.05, and so there's good statistical support that at an alpha confidence level of 0.05, it seems like we can probably say that there's definitely a statistical reason behind me saying this. I'm not just saying Texas has lower life expectancy. I've got a reason for it. In fact, if you look at most charts, you will find that this is the case. Not a lot, but a little. Texas has a slightly different life expectancy than the United States as a whole. If you segregate by states, you'll tend to find that many states have various life expectancies. Of course, this number comes up as creating the average of all the states. So we imagine that there's some states where people tend to live longer and other states where people tend to not live so long. Again, let me maybe end on this final note. There's two things. One, of course, is the null versus alternative hypothesis and our choice of alpha. I picked an alpha of 0.05 because 0.05 is common. It's the usual one we use as a default. I picked 0.05 and I'm not too worried about that choice because what's the worst that happens? Well, the worst that happens is I picked alpha either too big or too small and we've made some sort of mistake. If we think back to our chart, we've decided to reject the null hypothesis. So either we made the correct call or we've just made a type 1 error. In this case, we may have accidentally said that Texas has a lower life expectancy when in fact it doesn't. I can't really see much of a consequence to that. It's important to realize that statistics don't tell you cause and effect directly. I now have evidence that Texas has a slightly lower life expectancy maybe than the United States as a whole, but that doesn't tell me anything. I don't know why. We haven't gone into that. So before you pack your bags and move out of Texas, or before you pack your enemy's bags and send them to Texas, you need to think about the fact that we don't know what's causing this. It could have, in fact it likely does, have absolutely nothing to do with the geography. I have no reason to suppose that's the case. So instead you have to be wondering, what is it about these state lines? And many states have different cultures. Possibly there's something in Texas culture that is leading to these slightly lower life expectancies. We don't know. Well, maybe some people do, but from this data, certainly we just don't know. Contrary-wise, if you look at countries as a whole, the United States has pretty good life expectancy overall, but there's many countries that have better. Before you pack your bags and move to those countries and say, I'm going to live forever now, you want to be seeing, why do they have those higher life expectancies? My camera is telling me I'm just about out of battery, so I think I will leave you with that. Next time we're going to pick up and we're going to do the normal thing. We talked about something new. We had z-score for normal distribution, we had t-score for student t-distribution, and now we're going to have to talk about binomial probability. That's our usual three-step process that we do, and then we start talking about some pairs. Until then, be safe, and I'll see you in just a bit.